This meeting is being recorded.
In section 9.5, we're going to look at the mechanism and the reaction for the reduction of alkynes. And the first type of reduction we'll consider here is this catalytic hydrogenation. And we saw something very similar to this with alkenes. So in this process of catalytic hydrogenation, an alkyne will be converted to an alkane. And we'll see this percent yield 100% over here. So every alkyne will be fully converted to an alkane. And this is accomplished by adding 2 moles or 2 equivalents of H2 for every 1 equivalent of alkyne. So the first addition will produce a cis alkene. And this is because just like with the alkenes catalytic hydrogenation, we also see a syn addition, right? Just like with an alkene. So they are both added to the same side of the double bond, the same plane, and that's because of that metal catalyst holding on to those H2 atoms. So they are held on the same side of the bond, so they're added on in a syn addition. So we have a second addition, and then this would result in this full conversion or full transformation to an alkane. So if we want to stop the reduction of our alkyne at the cis alkane or alkene phase here, we can use what's called a poisoned catalyst. So we would add H2 across the triple bond, but stop after only 1 addition. So in green here, we see our cis alkene. And we would not go, we see this reaction stops, we would not go fully to an alkane. So 2 common catalysts that are used are Lindlar's catalyst and very uncommonly, you may see in the textbook, this other nickel-boron complex. But Lindlar's catalyst is given a full description down here. So we have this molecule here, this quinoline. We have a palladium and barium sulfate combination here, and then we also have methanol. So all of these combined give us Lindlar's catalyst or a poisoned catalyst in general. So let's look here at an energy diagram that graphically shows us how this reaction takes place. So our first step here, note that we have a blue line without the catalyst for step 1 and 2. Then we have this red line with a poisoned catalyst. And note that the first step will be catalyzed. So we have this lower activation energy, and then the poison catalyst does not catalyze the second step. So we have this high activation energy from our intermediate step here. So this is how the cis alkene is obtained, how we can stop at this intermediate by using a poison catalyst. The potential energy is too great with the poison catalyst to have a full alkane, so a full hydrogenation. And so the second type of reduction that we'll look at here is called the dissolving metal reduction. So this reduces an alkyne now to a transalkene. So a different mechanism that we'll look at step by step shows us using sodium metal and ammonia. And this, we should note, is different than the sodium amide that we saw before. That was acting as a base, whereas we're going to be getting electrons from these sources here with these solvents, these reagents. So we have our alkyne, and we introduce it to the sodium metal and ammonia conditions, and then we end up with our 80% yield for a transalkene. And we should note the terms we could use here are that this reaction is stereoselective. So the stereochemistry that results across the double bond is anti-addition of 2 hydrogens. So H2 is added in an anti. fashion. So let's take a look at the steps behind this, the mechanism. So step one here, we have a nucleophilic attack. And this is a proposed mechanism, right? So we're not sure if it's 100% true, but we're pretty sure. So first, when we have this nucleophilic attack, we're moving an electron from the sodium atom. So we see a fishhook here where we add this single electron. One of those triple bonds breaks, and we end up creating this radical, right? Because we see a single electron here, anion, because we have a lone pair. So this is what's termed a radical anion at this step here. Then we move a proton. In this next step, we have a proton transfer. So ammonia will donate a proton to the radical anion, and then we get this just radical intermediate because the anion has grabbed that proton, that lone pair, so that has been neutralized. So now we just have a single lone electron here, and then we have this next step here. We have another nucleophilic attack. This sodium acts as a nucleophile, so we move another electron here in this step, and now we have a lone pair that has resulted. And our last step will be another movement of a proton. We'll do another proton transfer and protonate our final product here, and we end up with this transalkene. So this walks you through in step by step. I'll move through this kind of quickly because we just looked at the steps, but the first step, remember, gives us a radical intermediate here, this radical anion intermediate, rather. Oh boy, that says cation here. So this should be anion, so I apologize. I'll update that in the slides for you. And then we have fishhooks used, so that's good to note as well. So in step one, the reason behind this orientation resulting, right, in our final trans fashion is that this radical anion is lower energy due to the repulsive forces that we would see if we had a syn addition. So we have this anti-geometry adopted. So over here we have anti shown. So we can take a look here at the next couple steps, and we see steps 2 and 3 happen. We have a proton transfer, we have a nucleophilic attack, and then we have this last lone pair here to be protonated in step 4, and we have our resultant product. So this is a summary of all the possible reductions that could occur with an alkyne. So we can reduce an alkyne to an alkane. So that's what we see all the way over here. Cis alkene, so that's up top. Oh, let me remove that arrow. So we have a cis here, and then our trans alkene we'll draw this arrow all the way around. So that's our trans down there. So the transalkene is at the bottom. So again, we start with the same starting material. If we choose the middle path, we would fully add 2 moles of hydrogen to our triple bond and result with an alkane product. If we took this pathway, if we took the top route, we would end up with our cis alkene, our intermediate, and then we could go one step further and then result in a full alkane, so full hydrogenation, right? So we have that option, right? So we could stop at the cis alkene up there, and then if we used our metal dissolve instead of a poison catalyst, if we took the bottom route, we would end up with the transalkene, and then once again we could add more hydrogen to that using a platinum catalyst, and then we would result with our alkane product. So we will continue with section 9.6 next time.